Now let's go ahead and look at collisions in 2 dimensions, okay? So this is where most of our real world stuff comes in, right? So what we will do is consider point masses. Okay, so what is a point mass? A point mass is going to be any kind of structureless particle that can't rotate or spin. So we're making sure that these are just points in space that if they collide, they don't spin or anything, they just move in like a 2D form. Okay, so no rotating or spinning. Okay, so think of the best, I think, would be to think of shoot, what are they called? Pool table, the billiards balls. I can't think of what they're called right now. For some reason, it is at a loss to me. Okay, but those will typically, when you hit them, they spin in all kinds of different directions, right? Well, let's consider them just moving on that pool table and not spinning or anything. Okay, so just moving. Okay, so that would be a point mass. So we've got point masses, and in our system of interest, we're assuming that our net force, our net external force is 0, okay? And that momentum is conserved. And we're also going to assume that our initial velocity of one of the particles is at rest. Okay, so again, kind of like playing pool, one of the balls would be at rest, okay, that you're trying to hit, right? So it's kind of like that, okay? So, and this is one of the ways I think that people would play pool, okay? You got to think of a lot of angles and such, right? So, excuse me. We are going to look at this diagram here, okay? And we're going to come up with a couple of equations that can describe the motion in the X and in the Y directions with momentum, okay? So in our before picture here, okay, we have a a point mass, a point mass that is moving with some velocity v1, okay, towards another point mass with velocity, oh, it already says it, v2 equals 0, okay? So this is our system of interest, and again, this is before the collision, okay? So our equation for our total momentum here is going to be our first potential, our first momentum P1, and our momentum of M2, so P2, okay? And remember that momentum is mass times velocity, okay? Now we have two different masses, M1 and M2, but V1 and V2 are different. V2 is actually 0, right? It's not moving. So P2 is actually going to be 0 as well, okay? So before our collision, the total momentum is just based on our first mass here, okay? So let me go ahead and point that out, okay? Now, these two point masses will collide, or M1, I should say, will collide with the M2, and they will go in different directions, okay, just like this says. And we want to understand the momentum in the X and the Y directions. Okay, so let's go ahead and kind of figure that out here. So again, after our collision, we will have some P total, and we'll have some P1 prime, right? The momentum after the collision of the first mass, and the momentum after the collision of the second mass. Okay, so we have our P total equals P1 prime plus P2 prime. Okay, and since conservation of momentum states that our momentum total before and after the collision should be constant, okay, remain the same. So in turn, we should have, let me put this up here, that P1 should equal P1 prime plus P2 prime. Okay, again, in this case where we have our second mass is 0, or velocity is 0 of the second mass. Okay. Okay, so now based on this observation here, we can start creating equations in order to describe the motion. Okay, so I'm gonna go ahead and put this down here. Okay, so before our collision, okay, so P1, to describe that motion, we have an XY coordinate system here. So our velocity was just moving in that X direction, okay? So if I'm looking at the X direction, okay, I have my P1 is going to be M times V1, or M1 times V1, right? And since it's along the X axis, I don't have to do anything fancy with it. Okay, that's all it is. Okay, now, after my collision, if I want to know what my P1 prime is, okay, I need to figure out my X position here. Okay, so if we're looking at this, and we want to know this here, we're looking at this triangle. Okay, we're given some theta 1. Okay, so we have our mass, and now we need to describe our x-axis here. Okay, so this side of our triangle is V1 prime. Okay, and this is our x. So what is it going to be? Using our trigonomic identities or understanding of trig, we can say our adjacent, which is this side here of the triangle, our adjacent divided by our hypotenuse, which is V1 prime, okay, will be equal to what? So we have adjacent and a hypotenuse. So that should be a C, so it's cosine, right? So we'll have that cosine theta 1 equals x over V1 prime. Okay, so then when you solve for x, this is what we're going to put here. V1 prime cosine theta 1. Okay, so that's for P1 prime. Okay, now we'll need to do the same thing with our V2 here. Okay, so our P2 prime is going to be M2 V2 prime. We make a little triangle here. It's again going to be adjacent over hypotenuse. So again, it's going to be cosine theta 2. Okay, so that's in our x direction. This is how they derived it. Oops. Now let's go ahead and do our y direction. Okay, now along our y direction here, or our y axis, you may notice that our momentum is, again, just along the x-axis. So there is nothing in the y-axis here, okay? So that means that there is no velocity in the y direction. So it's actually just 0, okay? And then we can do the same thing after the collision, okay? We have m1, and then if we're looking for a y here, it's going to be opposite now over hypotenuse, which is going to give us sine. So we're going to have v1 prime sine theta 1 plus m2 v2 prime. Again, opposite over hypotenuse. That will give us sine again. And we just derived this second equation here along the y-axis. Okay? All right. I know that was a lot. If you want to pause the video, take a quick break, feel free to do so. Okay, let's go ahead and continue here. If you are okay with continuing, we just have one more slide, but it does have quite a bit in there as well. Okay, so oops. Now let's look at elastic collisions of two objects with an equal mass. Okay, so we are going to assume that the second object is initially at rest, like we just had. So if we have 2 point masses here and here, this one has some v1, this one has v2 equals 0, okay? Objects 1 and 2 have the same mass, so m and m. Not M&Ms, but m and m. Okay, that was lame. Anyway, moving on. So we will need some equations to describe this motion, okay, for an elastic collision. So in an elastic collision, remember that our kinetic energy is constant, right? Or it's conserved. Okay, so before our collision, we have two kinetic energies, K1 and K2. But since the second mass is not in motion, we just have the kinetic energy of the first, which is here. So 1/2 mv1 squared. And after the collision, okay, so after they collide, boom and boom, now they're, well, actually, hold on. They collide, and then they go their opposite ways or whatever, okay, after they collide, okay. We have two different kinetic energies again after the collision. So we have K1 prime and K2 prime. Okay, so now we have, through a little bit of manipulation of, let me go back, these two equations, this conservation of momentum and along the x and y axes, okay, we come up with another equation here. And that is this here. Okay, now I'm not going to go into detail of how it gets here, but it's just through a little bit of algebraic manipulation, okay, and a little bit of trig background. I'm not going to go into it. I did it on my own time, and it was a little confusing and a little too advanced. But if you want to do it, feel free. But again, you do not have to. But through manipulating those two other equations, we also get this equation. Now, notice the only difference between these two equations. This term, right? So for this to be true, for both of these to be accurate and true, this term must be 0, okay? So this term has to be 0 in order for both of these to be true, okay? So if both of the, or I'm sorry, if this last term is 0, we need to check out what terms or what variables in this little equation here could be 0, okay? So our mass can't be 0, right? Because if the mass is 0, then none of these really do much, and then, you know, we can't really have that. Our mass must not be 0, so our mass is not 0, okay? Or else we wouldn't be looking at any kind of objects, right? There has to be some kind of mass to it. So it has to be one of these other terms, okay? So if we choose that our V1 prime is 0, this means that there is some kind of head-on collision and that the incoming ball stops. What does this mean? Okay, so let me draw that. Okay, so we have, again, this is our before. Whoops. That's our before image, right? Now after, if our V1 prime goes to 0, then our V2 prime is non-zero, okay? And we have something like this, okay? So it would just be a collision, a head-on collision, where the all of the momentum that was in the first one gets transferred to the second mass, okay? And so now V1 prime is at 0, okay? So equals 0, okay? So the other case would be that V2 prime is 0, okay? So if this point mass is coming into the second point mass, and even after the said collision happens, that velocity doesn't change in that second mass, right? It remains 0. That means that there was no collision in the first place. So this guy just completely misses, kind of a thing. So there was no collision, okay? So V2 prime equals 0, okay? In this third case, okay, where this cosine theta 1 minus theta 2 equals 0, that means that the angle of separation after the collision is 90 degrees, okay? So this means that now after the collision, this mass goes that way, this mass goes that way. So V2 prime and V1 prime, okay? And if I were to connect these, there would be a right angle here, okay? Or 90 degrees between them, okay? So that's what that means. Okay, so that's all the information I have for collisions and such. And so next I will go ahead and go through some examples with you guys.